Hello, welcome to 3.6, a summary of curve sketching. So today we're going to use the tools we have learned. We've been developing more and more tools, applying the calculus we've learned, taking derivatives and all that. We're going to be applying that now to sketching curves to get more to know what do we know about the curves, where should it turn, where's the max, where's the min, things like that. So, guidelines for analyzing the graph of a function. 1. Determine the domain and range of the function, always important. Determine the intercepts, asymptotes, and symmetry of the graph. So far, nothing calculus related. Locate the x values for which f prime of x and f double prime of x are either 0 or do not exist. Use the results to determine the relative extrema and points of inflection. So remember, our first derivative will give us the extrema. Second derivative will give us, at 0 is going to give us our points of inflection. So let's take a look at this first one. It says, analyze and sketch a graph of the function. Label any intercepts, relative extrema, points of inflection, and asymptotes. And so here's the graph from the calculator. And I think we can see from this, where's this denominator going to be 0? That's where x equals 2. That's what we have there. And then as x gets really, really big, 1 over infinity is 0, so negative 3y equals negative 3 is this horizontal asymptote. So that's a horizontal asymptote. Okay. And let's continue now. So if we have y equals x minus 2 to the negative 1 power minus 3, y prime is going to be negative 1 times x minus 2 times 1 to the negative 2 power. That's going to be negative 1 over x minus 2 squared. Now, so that's our first derivative. And from this, we have no place where it's going to be 0. We still have x being 2 is going to make the denominator 0, but that's not going to be a value that's in the original domain. So no extreme values, no extrema. Y double prime will be negative 2 times negative 1 times x minus 2 to the negative 3 times the 1, which is going to be 2 over x minus 2 cubed. Again, there's no place where this is going to be 0, so there are no inflection points. Now let's look for x-intercepts. That's going to be where y is 0. So if we put 0 in here, 0 equals 1 over x minus 2 minus 3. So 3 equals 1 over x minus 2. If we flip both sides, 1/3 equals x minus 2. So that x equals 2 plus 1/3, or 2 1/3. And that's what we have here. This point here would be x equals 2 1/3. That's that point. Or should I call that point maybe 2 1/3, comma 0. For the y-intercept, that's where x is 0. So y would be equal to 1 over 0 minus 2 minus 3. That's going to be 1 over negative 2 minus 3, so that's negative 3.5. So this point down here is going to be located at 0, comma negative 3.5. Okay, next thing. We have no inflection points, but we do have, no inflection points, but we do have to consider concavity. We could look at this graph and determine concavity, but let's just go ahead and test that anyway. So we're really looking at our interval from negative infinity to positive 2, and then from 2 to infinity. So I'll get our test value. Let's go with 0 here and 3 there. So f double prime of x, so here we're looking at f double prime of 0. And if you put 0 into this, it's 2 over 0 minus 2. That's going to be 2 over negative 8. That's less than 0, so that means you are concave down. As you might expect, this is concave down here. And then if you put in 3, you're at 2 over 3 minus 2. That's 2 over 1 cubed. 3 minus 2 cubed. 1 cubed, that's going to be 2. That's positive. So f double prime of 3 is positive, which means we're concave up. Again, as you might expect from this graph. So we have concave up, and here we have concave down. So concave up from 2 to infinity, concave down from negative infinity to 2. And that'll summarize that graph. Okay, I'm going to go on to example 2 here. So feel free to pause that one. Now for the next one here, we're looking at y, or h of x equals x times the square root of 9 minus x squared. And this graph does indeed stop there and there. It goes to that point, but it stops there at negative 3 and goes to positive 3. Because 9 minus x squared, you're looking for where this is going to be positive. So our domain here is going to be negative 3 to 3. Okay, so h prime of x is going to be what? X times 1/2 times 9 minus x squared to the negative 1/2 times negative 2x. So it's the first one times the derivative of the second one plus the second one times the derivative of the first. So h prime of x is going to be negative x squared over the square root of 9 minus x squared plus 9 minus x squared. Square root of 9 minus x squared. So where is h prime of x going to be 0? That's where 0 equals negative x squared over the square root of 9 minus x squared plus the square root of 9 minus x squared. So that's where x squared over the square root of 9 minus x squared, I'm subtracting this or adding this to both sides, equals the square root of 9 minus x squared. If I multiply both sides by the square root of 9 minus x squared, I have x squared equals the square root of 9 minus x squared squared. So x squared equals 9 minus x squared. 2x squared is 9. X squared is 9 halves. So x would be plus or minus 3 over the square root of 2. Okay? And we're looking at x being plus or minus 2.12. These are the critical values. As for our second derivative of this part right here, we're going to do low d high, so it's going to be the square root of 9 minus x squared times negative 2x minus high negative x squared times this derivative is going to be, again, 1/2 times 9 minus x squared to the negative 1/2 times negative 2x over, oops, I'm writing this on the computer. I could just hit undo that line, but I can't do that here. all over the square of what's below, so it's the square root of 9 minus x squared squared. Okay, so our h double prime of x is going to be oh, I forgot this other part here. The derivative of that part. Plus 1/2 times 9 minus x squared, negative 1/2 times negative 2x. Okay, so h double prime is negative 2x times the square root of 9 minus x squared plus, now I've got negative, 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 so it is minus. This 1/2 and the 2 cancel, so we have x cubed over the square root of 9 minus x squared all over the square root of 9 minus x squared squared minus x over the square root of 9 minus x squared. So I'm going to multiply on top and bottom this part here by the square root of 9 minus x squared. H double prime of x is going to be negative 2x square root of 9 minus x squared times the square root of 9 minus x squared minus x cubed over the square root of 9 minus x squared times the square root of 9 minus x squared over the square root of 9 minus x squared squared times the square root of 9 minus x squared. So what I've done is I multiplied everything in the numerator here and everything in the denominator by square root of 9 minus x squared, so effectively multiply it by 1. So minus our x over the square root of 9 minus x squared. This is going to give us h double prime of x equals 2x. I'm showing on my notes the negative went away. I don't think that that's right though. Just double checking. Back here, this derivative is negative 2x, so it's low d high. So yeah, that seems right. I'll start right here. Okay. So h double prime is going to be 2x times 9 minus x squared minus x cubed from this part, so all over the square root of 9 minus x squared cubed. And then we have minus x over the square root of 9 minus x squared. So just to finish that off, h double prime of x is going to be 18x minus 2x cubed minus x cubed over the square root of 9 minus x squared cubed minus x over the square root of 9 minus x squared. And that's going to be 18x minus 3x cubed over the square root of 9 minus x squared minus x over the square root of 9 minus x squared. I need a little more space, so feel free to pause if you need to. I'm going to bring information I'm going to erase here and come back up there to continue working. And on this one, I think I want to multiply this by 9 minus x squared. And if it helps to see it this way, think of it as square root of 9 minus x squared squared over the square root of 9 minus x squared squared. So pause if you need to pause. I'm going to erase and move on to the next part, continue this on. So h double prime of x is going to be 18x minus 3x cubed. And this should have been a negative here, so that makes this a negative 18 and plus. Oh, that changes things, doesn't it? That changes things a lot. That makes this just 2 plus x cubed. Okay. Over the square root of 9 minus x squared cubed minus, and this is x times 9 minus x squared, so 9x minus x cubed over 9 minus x squared, square root of that cubed. So if we combine these, we've got to distribute this negative. H double prime of x is going to be 18x plus x cubed minus 9x plus x cubed over the square root of 9 minus x squared cubed. So h double prime of x is going to be 2x cubed minus 9x over the square root of 9 minus x squared cubed. Now the denominator still is that same problem we had before as far as domain. We have that same domain. So look at the numerator. Where's 2x cubed minus 9x going to be 0? That's where 2x, now x times 2x squared minus 9 equals 0. So that's where 2x squared minus 9 equals 0. So x equals 0, or 2x squared minus 9 equals 0. So 2x squared equals 9, x squared equals 9 halves, x equals the square root of 9 halves, which is 3 over the square root of 2. That looks familiar, huh? Where x equals 0. Those are potential for inflection points. But given that this was 0 for the first derivative, means it's not going to be an inflection point. Okay, so okay, where should we go with this? We can make a little chart here. We have some intervals to consider. We have from negative 3 to negative 3 over the square root of 2. We have from negative 3 over the square root of 2 to 0. We have from 0 to negative 3 over the square root of 2. And we have from positive 3 over the square root of 2. So from 3 over the square root of 2 to 3. So let's get a test value. So we can go like negative 2.5 should work. That was negative 2.12, so that should work. And here we can go with 1, go negative 1, go with 1 here, and then 2.5. So now we're looking at f prime of x. And we'll look at f double prime of x. And then we can draw some conclusions. Okay, so if we look at f prime of x, and I shouldn't say f, I should say h. And remember our h prime of x was negative x squared over the square root of 9 minus x squared plus the square root of 9 minus x squared. Now if we put negative 2.5 in here, the denominator is going to be positive because it's 9 minus something smaller, but the numerator is going to be negative. And then we have 9 minus the x squared. So I'm going to get my calculator here. So what I'm going to show you now is I can use this calculator, put it in table mode, And I can get these values. So I programmed in my calculator the first derivative and the second derivative. And a really neat way to do that is by taking the derivative with the T89. You can put the original function in, take the derivative, copy and paste it into your y1, take the second derivative, copy and paste it into y2. So let's put in some values. How about negative 2.5? H prime of negative 2.5 is going to be negative. H double prime of negative 2.5 is going to be positive. So that means we're concave up. Yeah, it certainly looks like it, concave up. And then let's do negative 1. So H prime of negative 1 is positive. H double prime of negative 1 is also positive. Okay, so that means we're still concave up. So we're concave up. It's decreasing here. And it's increasing in the next interval. That means it went from going down to going up, so this means that's a minimum. So negative 3 over the square root of 2, comma h of negative 3 over the square root of 2 is a minimum. Now let's look at putting 1 in there. Our first derivative is positive. We can see that it's still positive, it's going up. Our second derivative, however, is negative. So that means we're concave down. We're increasing. And then let's put in 2.5. Our h prime of 2.5 is negative. Our h double prime of 2.5 is still negative. So that means we are decreasing and we're concave down. Okay. That means it was going up then going down, so we have at negative 3 over the square root of 2, comma h, now positive this time, 3 over the square root of 2, that's a maximum value. So we have a minimum here and a maximum over there. Min and a max. What happens here at 0, 0? H of 0 is going to be 0. That's going to be an inflection point. Why do we know that? Well, it changed from going concave up to concave down. That's what an inflection point does. Okay. So, to finish this off, erase some over here. We have an inflection point at 0, 0. We have a maximum at 3 over the square root of 2, comma, if we plug in the numbers, it's 4.5 roughly. And we have a minimum at negative 3 over the square root of 2, comma, negative 4.5. And we have no asymptotes, and that's it. I guess we have an x-intercept at 3, 0, and negative 3, 0, and 0, 0, and that's also the y-intercept. Okay. That was a long problem. It's going to be kind of a long section, so let's get on to the next part. Feel free to pause if you need some more time. Come on, if I can get that. There we go. So this one says, analyze and sketch the graph of the function, label any intercepts, relative extrema, points of inflection, and asymptotes. Okay, so our first derivative is 4x cubed minus 12x squared plus 16. And our critical numbers, if we 4x cubed minus 12x squared plus 16 equals 0. If we divide everything by 4, it's x squared minus 3x cubed minus 3x squared plus 4 equals 0. So that would be x plus 1 times x minus 2 squared equals 0. So our critical numbers are x equals negative 1 and x equals 2. Now, for the next part, let's find our second derivative. This function is a lot nicer to work with. F double prime of x is going to be 12x squared minus 24x. So if we set that equal to 0, 12x squared minus 24x equals 0. So it's 12x times x minus 2 equals 0. So from that, x equals 0 and x equals 2 would be our potential. These are the potential inflection points. Doesn't mean they're going to be that. Now, here's our graph. So we're going to have intercepts. Maybe we should find those intercepts. Where is x to the fourth minus 4x cubed plus 16x going to be 0? And at this point, I really don't think we need to go back and have to reinvent the wheel. On our calculator, we have tools to use. And if I go into F2 has algebra tools, so we could find zeros. If I type this in there, x to the fourth minus 4x cubed plus 16x, and comma x means I'm going to factor with respect to x, find the zeros for x. Our zeros are going to be at negative 1.6778 and 0, comma 0. Those are the zeros. And we can kind of see that there. We see those zeros. And that's going to be our x-intercept, and this is also the y-intercept. Okay. I did that because I'm going to have to scroll up now. We're going to take these values that we have. We have the critical numbers, negative 1, 2, and these numbers 0 and 2 for our look to explore for our first and second derivatives to find where we have concavity changes. And if you look at this, you can kind of guess. I'm just looking at this without looking at the answers. Concave up here, it looks like it changes concavity at 0. That's where it kind of goes to be facing down. Then at 2 it changes concavity again. So my guesses are going to be that we're concave up from negative infinity to 0, concave down from 0 to 2, concave up from 2 to infinity. That's my guess. We only have one extreme value, and that's down here at negative 1. So given that visual inspection of this, we'll see what happens. Let's look at this chart down below we're going to be completing. So I've kind of changed the format of our chart a little bit to where we have the original function, first and second derivative, and a conclusion. And we're going to have our intervals over here. So we have negative infinity to negative 1, because that was a critical value. We're going to see what happens at negative 1. We're going to go from negative 1 to 0, because that's another critical value, or a value in question. We're going to see what happens at 0. We're going to go from 0 to 2, see what happens at 2, and then 2 to infinity. I should have had one more column here for test value. So when we have an interval, we need a test value. Like here we could say -2. Here we could say x equals -1/2. Here x equals 1. Here x equals 3. So we really want f of x at the specific values here. So f of -1 is going to be -11. F of 0 is going to be 0, and f of 2 is going to be 16. Now for the first derivative, if I take this test value for the first derivative, I want to see is it positive or negative. Here, f prime of -2 is going to be negative. So that means that it's decreasing in this interval. For this interval, no, that's 0 there. F prime at -1/2 is positive, means it's increasing there. F prime at 0 is going to be positive as well. F prime at 1 is positive, and F prime at 2 is 0. This could have been a max or a min, and it's neither going to be max or min. And F prime at 3 is still positive. So we know that it's decreasing at one point, then it's just going to be going up with a place where it stops off at 0. Now f double prime of x, taking the second derivative, f double prime at -2 is positive, so that means we're concave up. F double prime at 0 is positive, which means this is a minimum value. Because the second derivative is positive there. Means it's concave up. F double prime of -1/2 is positive. So continuing up the interval. Now f double prime at 0 is going to be 0. That makes it a point of inflection. How do I know that? Well, we saw the shape, but what happens to the next one? F double prime at 1 is going to be negative. That means it's down. It's concave down now, and f double prime at 2 is going to be 0, and f double prime at 3 is positive. So we're taking values from the given interval, which makes this a point of inflection. So in this interval, f of x is decreasing and concave up. In this interval, f of x is increasing and concave up. In this interval, f of x is increasing, but it's concave down. In this interval, f of x is increasing, and it's concave up. Okay. Whew, that was a lot of work. Let's go on to the next page. Okay, example 4. It says sketch the graph, and it's already sketched there, of the indicated function over the indicated interval. And here it is, from -pi/2 to pi/2. Y equals 2x minus tangent x. So our first derivative, y prime, is going to be 2 minus secant squared x. Now 2 minus secant squared x equals 0 whenever 2 equals secant squared x, or 1/2 equals cosine squared x. or where the square root of 2 over 2 plus or minus is cosine of x. So x would be negative pi over 4 and pi over 4. So right about there and right about there. And it kind of looks like we have a max and a min there. Y double prime would become, this just 0, this becomes negative 2 times secant x times the derivative of secant, because it's like a chain rule thing, it's something squared, which is secant x tangent x. So it's going to be negative 2 secant squared x tangent x. So where is negative 2 secant squared x tangent x equal to 0? Well, secant's not going to be 0. Tangent x is 0 whenever x equals 0. And that definitely does look like a change of the concavity from concave up to concave down. Okay, so we're going to have an interval, a test value, f of x, f prime of x, f double prime of x, and a conclusion. Okay, so we have the interval from negative pi over 2 to negative pi over 4. We have it from, we'll look at what happens at pi over 4, negative. Make sure we have enough space here. We have from negative pi over 4 to 0, and we have what happens at 0. We have from 0 to pi over 4, what's going to happen at pi over 4, and we have from pi over 4 to pi over 2. Just squeeze that in there. Look at that. Now our test values. Value in here, we can do negative pi over 3. We can do negative pi over 6. We can do pi over 6 and pi over 3. So f of x, f of negative pi over 4, if I plug this in to the original function, I'm going to get negative 0.5708. If I plug this one in, I'm just going to get 0. If I plug pi over 4 in, it's going to be positive 0.5708. Now look for our first derivative, and we're looking for it being positive or negative, except for these critical values. We know it's going to be 0 here and here, because those are critical values. Those are potential maxes and mins. So f prime of negative 3, that's going to be a negative value. F prime of pi over 6, that's going to be a positive value. F prime of pi, sorry, that's negative pi over 6. F prime of positive pi over 6 is still a positive value. And f prime of pi over 3 is a negative value. So what we see is that it's decreasing then increasing, so that makes this value here a minimum value. And this goes from increasing to decreasing, makes this one a maximum value. Okay. Now let's look at the second derivative. If I were to plug in negative 3 into the second derivative, we would have a positive value. If I plugged in negative pi over 4 in the second derivative, still a positive value. So that's a second derivative test. That confirms what we had. It's concave up, which makes this the minimum. Again, positive for that value. If I plugged in 0, I'm going to have 0. If I plugged in pi over 6, this will be negative here. Plugged in pi over 4, negative, and still negative. Now, given that's negative here, means that it's concave down. This is a maximum. So it's concave down for this whole area. So we have, this is decreasing, concave up, This one is going to be, it's a relative minimum, and still concave up. This is going to be increasing and concave up. This is going to be, now look, it went from being concave up to concave down, so that makes this an inflection point. Now it's increase and concave down. Forgot to turn my phone off, sorry about that. And here it's decreasing and concave down. Okay. So we have our relative max at pi over 4.5708. We have our relative min at negative pi over 4, negative 0.5708. And we have an inflection point at 0, 0. That'll do for that section, or that problem, not section. We still have a couple more problems to go through. I know it's a long section, bear with me, we'll get through it. But 2 more examples. So feel free to pause if you need a pause. I know it's a lot of information. This is all in the notes though. Moving on. Okay, example 5 says, use a graphing utility to graph the function. Use a graph to determine whether it is possible for the graph of the function to cross its horizontal asymptote. I think we can see that pretty well. Do you think it is possible for the graph of a function to cross a vertical asymptote? Why or why not? Well, so here's our function 4 times x minus 1 quantity squared. This is going to yield in the numerator 4 times x squared minus 2x plus 1 over x squared minus 4x plus 5. That's 4x squared minus 8x plus 4 over x squared minus 4x plus 5. So the horizontal asymptote is going to be y equals 4 over 1, which is 4. And we see that here. We see that that's y equals 4 there. So yes, it is possible to cross the horizontal asymptote. Now, if we were to look for the vertical asymptote, that's where x squared minus 4x plus 5 is 0. So we look for x equals the negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1. This is going to be 4 plus or minus the square root of 16 minus 20 over 2. That's 4 plus or minus the square root of negative 4 over 2. 4 plus or minus 2i over 2. So it's 2 plus or minus I. Now that's not real, so there's no vertical asymptote. But you cannot cross a vertical asymptote. You can cross a horizontal asymptote. Why? Because the horizontal asymptote indicates where it's going to go in the long run. It doesn't necessarily apply to what's happening here. For vertical asymptote, you can't cross it because that wouldn't make it a function. Okay. Let's move on to our last problem of this section. So feel free to pause. I guess now feel free to back up. And it says, create a function whose graph has the indicated characteristics. Vertical asymptote at x equals 5. Slant asymptote at 3x plus y equals 3x plus 2. So 1 over x minus 5 is going to be part of it. That'll give us a vertical asymptote. Okay, now if we said y equals 3x plus 2 plus 1 over x minus 5, as x gets really big, this part becomes nothing, and this takes over. So it's going to be approaching this line. So if x is very big or very small, this is insignificant, it's nothing. We can go further, we can say, okay, y equals 3x plus 2 times x minus 5 over x minus 5 plus 1 over x minus 5. So y equals 3x squared minus 15x plus 2x minus 10 over x minus 5 plus 1 over x minus 5. Y equals 3x squared minus 13x minus 9 over x minus 5. And now we can say we're finished with this section. I know it was a long section and we did a lot of work, and I hope you see all the details there. And I'd be happy to send me an email if you want me to set up something to show you. I can just do a little video with the, not seeing me, but seeing the calculator to see how we can do the tables. It's a very useful tool. I encourage everyone to have a TI-89. They're very good calculators. So, okay, thank you. Send me your questions. Bye.